My name's Chris Ryan. I am not a 3D graphics expert. I play one on stage sometimes, but this is something I just do for the fun of it. It all around engineer. Gee, where'd my clicker go? The previous slide bait. This is what most of my slides look like. We're going to cover 2D points, 3D points, and vectors. Describe the difference between a point and a vector. Polygons, little asterisk at the bottom first. Everybody in 3D graphics uses their own terms for lots of different overlapping terms. I may intermix between some of them. I hope that doesn't get too confusing. Most of the concepts are actually very simple. Normally in 3D graphics, you want the oohs and the ahs and make it scary sounding, so you pay the graphics people a whole bunch. It's simple math. This has got a bunch of fancy names behind it, like some linear algebra. But we're going to handle some matrix math, matrix transforms, and how we change dots, pixels, in three-dimensional dots, and rotate them around, move them, that type of stuff. We're going to learn a little bit about the difference between when you transform it from a model to a world to a view and then the screen and then the matrix operations that do all those. We're going to talk about surfaces or textures. That's what you paint the surface with. They call them textures, but they're flat. We're going to learn what rasterization is and how that's actually done. We're going to do when you take a 3D set of coordinates and you squish it and you flatten it to a 2D and how that gets on the screen. There's something that my little demo app here has, which is a affine perspective interpolation error, also called derivative discontinuity in interpolation, and show you why some of my math doesn't quite jive up and a couple ways to get around it. I don't know all of the fancy math. There are other ways of doing it, but it's much more expensive math operations. I'm going to describe what a depth buffer is. Whoops, get back there. And the actual display buffer. And if we have time, I'm going to talk about a couple multi-threaded optimizations. I was classically trained in hardware and software. My primary language is C++. There's a little demo app I have is in C++. It's incredibly huge, 1,500 lines. The executable is 56K. Not 56 meg, 56K. That's the whole thing. And that's including a little bit of the app that's actually a Windows SDK that's the framework for driving this. I do not use a third-party rendering library or coordinate stuff. I'll do all the math, everything myself. The only thing that I don't do is bit-blit on the screen. I make a bitmap and tell Windows to bit-blit it on there. I've worked in extremely large, complex problem spaces. I don't like the word complex. I think if it's complex, you're not doing it right. It should be simple. I mostly history of working in DOS, Windows, and embedded. I know some Linux. I'm not an expert at it. I've worked in many different domains. Some things will not cover in very much depth. Multi-scale surface or texture options and ways of dealing with those. I may throw a couple of them at you. Not going to handle a whole lot of dealing with light sources or aliasing. And you may have heard of aliasing in other graphics when you have a diagonal line that goes from here to here. Rather than just having a square stair step, interpolating pixels on either side to soften up the edge. I'm not going to bother dealing with that. Where did you go? Okay. Some of the stuff that you'll see on the screen will drive your mind crazy. I'm going to have some graphics where objects will be appearing to collide and actually go inside of each other. The human mind doesn't like that, but that's because my graphics engine that I wrote for this does not have a physics engine in it and doesn't understand collisions. Points are points and it just draws between the points. But it was actually a demonstration that shows how the depth buffer works on every pixel. So there's some other vector math which I'm not going to cover, but in theory, experts may use some of that. I didn't. Okay, you have a 3D shapes. How do you draw a 3D shape? We don't have nice curves and smooth edges and stuff like that. We do it with lots of different triangles. And each triangle, but also called polygon, has a surface that gets painted on it. More and more triangles you do, the more simulated the shape is. So all the triangles are called edges and vertexes. Vertexes are the points in 3D space that we map. The edges are just imaginary lines that connect these. So even though that's just some crude triangle drawings, you can recognize that that's a dolphin. The more triangles you use, the more smooth of a surface that it looks like you get. So the first one you can almost tell it's a rabbit, but by the time you get to the end, if you had enough colored surfaces, that would look like much more like a rabbit. You've probably all seen the classic teapot. This is wireframe, typically. There's squares on here. We don't really do squares. You can do squares with wireframes if you want to just see the silhouette around it. We do lots of triangles. So why do we do triangles? 3 points define a plane. If you have a fourth point, you don't know it's on the plane. And then when you try and paint a flat surface between those 3 points, you can't bend it around the corner. So we just go 3 points. And it's the interior area there, even though it defines the entire plane. A point is just a spot off of in a coordinate plane. It doesn't represent anything other than a position. A vector represents a direction and a magnitude, but not the starting point. If you can add a vector to a point and move a point, you can subtract 2 points and get the vector between them of how to get from one to the other. You can add and subtract vectors, and you basically just add them head to tail, and that makes a new vector. You cannot add points. That would make no sense. Points are stored. We have an X, Y, and Z coordinate, but we actually store them in a 4x1 or 1x4 matrix, depending on how you call it. Points out of math correctness and a way to tell which is which is we write a point with the y or the w parameter is a 1 and a vector with a 0. If you end up subtracting 2 points, that one, the one at the end, when you subtract that off, that ends up as a 0, and it shows you have a vector. Through the C++ I keep it type safe also, and all my operators know which you're subtracting and what it does and returns their proper type. But if you just had a 4x1 and you didn't know if it was a point or vector, you could look and see, based on if that was a 1 or a 0, if it was a point or a vector. Matrix multiplication, that's mostly what we end up doing. And you probably had to do some of this in junior high math, maybe freshman or sophomore in high school. Basically, you just end up your x times each of the first column, your y times the second, z times the third, m times the fourth. It's written out this way, and this is a 4 parameters in parentheses that are clustered together into this new vector. If you're going to multiply a 4x4 array, that gets a little more complex. And you would think it takes up a lot of time to do number crunching. It's actually not too bad. It's all of the first row times the second, or times the first column, first row times the second column, on and on and on, until it ends up with producing a new array that's a 4x4. Internally, I store a matrix is an array of floats, is a 4x4 array. The reason we use floats is they're relatively fast internal inside of the hardware of the CPU. You think you might, a float is 4 bits. You might think you would want to use 8 bits for more accuracy. If you're dealing with numbers of that much, you don't need that many decimals and that much huge of a mantissa for the significance on it, so that's fast enough. Also, for transferring back and forth to a GPU, if you're going to do the math in a GPU, it natively knows floats, and it does good enough on those. You could actually, modern GPUs can do doubles, but it's overkill there, and it's double the transfer time of in and out of memory. So, and that becomes significant. For points and vectors, I have a base class that I call data 4. All my own made-up mechanisms, and it's just 4 points or 4 coordinates, x, y, z, and w. I derive from that, and I have a type-specific vector and point, and each of these has they're not yet operators; they're just functions. You can do cross products, and you can add and subtract and multiply these, and they all come out as type correct. C++ is very type sensitive, and to protect you from yourself, you can't get the wrong answer back when you're multiplying or adding different types. The main operations that you're going to do with matrix on these is you're going to scale. You're going to make something bigger or smaller in different coordinates. Translate is to move it from one point to another. Rotate around the x-axis, y-axis, or z-axis. And orthonormal basis, I'll show you a picture of that. It's a big word. It doesn't mean much. So, scaling. X, Y, and Z. You have something that's a small object and you multiply it out. Whoops. Oh, another thing that, and we'll hit this occasionally, standard convention is your objects you deal with are typically between 0 and 1, plus or minus. So, unit 1, measurement. You want that bigger, you can multiply in different directions, and you can squish it also. So pretend this is the same model. So it's flatter, longer, wider. We've placed it on there. You want it even bigger? You just multiply it and stretch it. Every object has its own origin, where it considers its center. Because when you want to scale something and you multiply that, that's where that is taken effective. Or when you move it, that's where it's done. When you rotate it, it rotates around the axis. So we've got bigger objects and flatter. And another one too. Pretend they all have the same skin surfaces on them. So scaling, you can multiply x, y, and z at the same time in different amounts. They don't have to be linear. So that's how you can make something wide and flat at the same time. Translating is you say, I want to move it to this coordinate. Relative to the object's origin, you move it laterally or in z space or wherever you want. Rotating around the object's origin. Easy to make the object origin in the middle, and it's around the x-axis, y-axis, or z-axis. Now, this isn't going to make a lot of sense yet, but if you have something that's existing in this point in space out here, sometimes you want to look at that from a different perspective. And so you want it to have its own different axis basis. So all of a sudden, now this object's sitting here, and it's stored in these coordinates. You can translate that into x. Well, this is x, y, and z. Nomenclature for this varies, but it'd be u, v, and n. Origin to origin matches up. So the origins, the 0, 0, 0, are going to be in the same spot, but it's now going to be potentially twisted. And we'll show you in a little while of how you would potentially do that where you're not doing it from a twisted, you're actually dealing with a different new origin. To combine some of these operations, you can multiply the matrix together and then multiply the matrix times the point and do that more as a collective operation. But it's order sensitive. So you got your object is living at the origin, and you want to move it laterally and then rotate it. Did you really want to rotate it and then move it laterally? Or actually rotate and then laterally. So it's order sensitive. And you can see in the diagram here how that ends up making a difference if you do one versus the other. Matrix multiplication is basically left to right, and I call this V for vector. Vectors or points are the same, mathematically the same difference. And if you have your M1 matrix, let's say, is a rotate, and then M2 is a translate, and M3 is a scaling factor, it would take the point or vector times M1 and then multiply it times M2 and then times M3. If you had a whole bunch of points you were doing this to, that's 3 matrix operations you're doing for every single point. But if you can combine all these matrices in order, M1, M2, M3, into a single matrix just called M, then you can multiply it times that point, and you can go through your whole list of points and multiply that one simple matrix against your entire list of points. And that way you didn't have to do M1, M2, M3, M1, M2, M2, M3, etc. And therefore you've just done 1/3 as much math. Okay, I'm not going to really talk about vector scaling or vector length. What normalization means, that's basically converting it just a unit length to 1. There's important reasons to that. What cross products are, or dot products are, and why they're useful. Or why do we want to square up vectors? Okay, a model has surfaces on it. We don't really care what's on the inside. There, as far as we're concerned, there is nothing on the inside because you can't see it. You only see the outside surfaces. A model is a collection of polygons, or the triangles. Some people call this a 3D object or just simply an object. The code for that is a triplet of points, the 3 different coordinates that form the triangle. And this is just how I've done it for my little program. I'm not trying to sell you the use of mine. This is just for modeling so you'll understand how it works. A surface ID is what we're going to be painting on there. And it actually has a sub ID also, and you'll see that coming up in a couple slides. A mesh is a collection of points. So that cube we were looking at is a series of triangular surfaces on there that we're going to paint on there with this up arrow, and the leftmost, my dyslexia is striking in reverse directions here, is what the actual surface is. It's a bitmap of an up with an arrow on it. And since we don't actually do squares, we're doing triangles. We cut it in half. We have 2 different triangles. All of the examples I've used in my stuff I'm doing here are right angle triangles. They do not need to be right angle triangles. If you have some really irregular shape, like a soccer ball, and you subdivide that up into a lot of different triangles, you're not actually going to end up with no right triangles. That doesn't matter. The triangles here are the coordinates on a plus and minus 1 cube, and this is one surface on that. This is what a surface looks like, and a surface has two different parts to it. This would be 0 and this would be 1, and these are the coordinates that map it into the 2D coordinate system here. Back to what my mesh is. A mesh is a collection of all these polygon objects, which have the triplets of points in them and the surface ID. When we multiply a matrix onto a mesh, it goes through every polygon in its collection in the vector, and then it multiplies every point, each of the 3 points in each of the polygons. Okay. This is a cubical Earth globe. So it's the same idea, very similar cube. We've got the ID of this, and then each of the different surfaces we're going to paint on here. And this would be surface 2, and surface 3, and 4, 5, 8, and 9. And the coordinates for each of these are in this table, and the index is implied for which surface they are. So a surface doesn't have to be exclusively only a single triangle or even just two triangles. It can be an entirely large bitmap and with void space, or sometimes if you really want to reuse space, you could put dummy data in there and use other images in there just to conserve space. As it is, what I've done is just black space. Okay. A model is the 3D object. There's all the triangles on the make up the different sides and how they would end up getting painted with the ups from each of the different surfaces. This happens to show the side's darker because there was a light source from the other side. I'm not really going to handle much worried about light sources at this point, but if we want to, then we can talk about it later about how simple it is to handle some of that. Each model has its own coordinate system that it's based on, where its origin is. But the first thing you want to do is place it in a world. The world, everything has its own new origin. So we've started its origin, we moved it, and we maybe elevated it. I can't let this thing float forever, so we'll say we placed it there. We make another copy of that model and move it and rotate it and put it over, in its own space. We do this again, and this time we actually rotate it. Hopefully it doesn't roll off the table, as that one's going to lie down. Come on, my clicking is driving me crazy. Model space. So each model has its own matrix of where it's moved to. Translate, and if scaling, rotating. So I don't have a much larger bottle, but if we scaled it, we would have a monster bottle, or potentially a little teensy one. And it's placed in the world, and it's based off the origin of what you're calling the world, and potentially we're not going to really deal with it, but there's a light source that's going to be shining on this. We're not going to really handle that, but other 3D engines do. And so there's bright sides and shadows on this. I'm not going to be handling transparency. These bottles are transparent, and that adds some little more complications. But that's just painting tricks. So the coordinate space we have the model space, which is the coordinates that the model itself uses. And then when we move it into the world, and then where we're viewing it from, your camera, your point of view, and then so that's kind of going from, how do we describe it? It's in the, model space is each object having its own coordinate system. The world is the world space that we're dealing with. The view space is where you'll be viewing it from a perspective. And then the screen space is when we've skewed the perspective based on depth, and it kind of squishes it so that even if things that are the same size, when they're further away, they actually look smaller. So you can kind of see in this diagram on the screen here, the back triangle on that cube is a little bit smaller than the close one. And I'll show you how we do that. It's just yet another set of matrix multiplications we do. So the view space is wherever we're viewing from. We're going to be viewing from out here. And our camera has its point of view of how it's going to be looking at this. And so when we're talking about that, redoing the coordinate system on that, that's basically this again, but the origins aren't the same. We do the origin translation, and then we translate where its center is. I'll show you the math on that in a second. View space. Okay, so this is going world space to view space. That's where we tilt it and we're looking at it from an angle. We haven't done the perspective view on it yet. So the depth it's in Z, but it's not squished together. The depth doesn't make things smaller yet. That's where screen space is. When you have a camera and you're looking at something, you have your view that you're looking at that has a certain angle that you're looking at it. And there's a front clipping zone and a back clipping zone. Anything closer than this you want to ignore, anything further away you want to ignore. But your view of the size of what's behind you, the furthest away, is actually much wider than what you're seeing close. But that also means something that's further away of a unit size is much smaller of a percentage of the full view. So that's why something further away looks smaller, because it's a smaller percentage of the back plane. There's 3 different matrix operations that happen for this. From the point of view, field of view, and the viewport, I combined those into a single matrix operation. And I do that just to create a single matrix that I can do this transpose from. Part of what's involved in this is the point of view is where am I viewing it from? What direction am I? Because I could be right here, but there's nothing saying I'm looking over there. I could be doing my viewport looking over here, and I'm not going to see those. Also, which way is up? If I'm looking at something and then turn my camera or my head, the objects look like they're going a different direction. So we have 3 different vectors that take that into account. So we have the point, the view, and the up. I kind of think of it this way. You use the thumb being the up, and that's the direction I'm pointing, or the way things are going to be. Okay, we've seen this before. This is just the transitions we're doing again. World matrix, you rotate your object and you translate it, and you multiply those matrices, and that's your matrix for multiplying against the points of an object to move it to where you want in the world. And the transformation pipeline is you, from model space to world space, camera space, perspective space. There's some clipping operations that you can do. I've actually skipped those. And homogeneous screen space is an extra divide operation that happens. And the points, once you've scaled them and done all this math to them and the point of view and stuff, the W parameter for points is no longer 1. It's some funky number that we end up going through and doing a perspective divide on, and we'll hit that in a minute, that scales things for perspective view, that makes the further away something is, that makes it smaller looking. Okay, here's the world space, the view space, where we have the multiple axes. We have the axes of the origin of where things are at, and then the origin from the view of the camera. And so we got X, Y, Z, U, V, N for these vectors. And then we have the X, Y, and Z that is the origin of where the camera space is at. Now, we really didn't look in too much depth of when these before, but the X, Y, and Z on the bottom there, that looks a lot like when we were doing the translating of moving something between different positions. And these matrices, the UVN is a lot like when we translated the origin there. And they are. These are the two different pages. And we had the translation matrix and the orthogonal normal basis. And if you notice, this matrix looks a lot like this one, plus a lot like this one. And there's some complicated math behind how that works. But you can see that that's actually how they're doing these in one operation. Internally, somebody figured out that you can multiply these together and that it works out to be this way. So you don't actually have to do two separate matrix operations, that it's all combined. Some of it's magic. You have to just kind of accept it works. Okay, our perspective view, we talked about that a little bit before. It kind of has its own coordinate system. Now, these show the X, Y, and Z axes having arrows on them going different directions from different origins. The emphasis of the direction of the vector of your axes is more of convention. Every system uses different coordinate systems of which way they consider up and for X and Y and Z and where the origins are. It's whatever engine you're using of how it will be set up. I'm not even sure if this is the same as mine. This is some slides, like pictures I had borrowed. The field of view we were talking about from the camera, we were looking at there. The math on that is the field of view and then the aspect ratio of what window you're going to project this into on your screen. Is it a 4 by 3, a 19 by 16, or whatever that is? The last step of the pipeline is perspective divide. So we divide the X, Y, and Z by the W parameter in each point, and this scales the depth appropriately for you. This is even more magic. I don't even know the math on this one, but it works. These are all the different math operations that my library that I wrote for myself handles. All the basic types of points, vector, matrix, and meshes. And I have multiple versions of meshes, of worlds and screens. Those are all different meshes that I can multiply matrix upon. I just changed the name on them through using. But you can multiply a vector times a matrix, point times a matrix, matrix times matrices, and then a matrix times a mesh. And a mesh is the collection of all those different polygons. And if you actually had multiple objects, when you place them into your world, you've added them together, and that's kind of in the whole world mesh of there's now all the polygons that define each of the different pieces of candy and the water bottles and where they were placed. And so those are all in the same big uber mesh. And so when you multiply a matrix against that mesh, every single point in there gets multiplied across this. If you have millions of points, that's millions of matrix multiplications you have to do, which is why you'd want to combine all your matrices and not do them repeatedly. That combining I showed you before. Another form of the types on these, and the types are correct. The mesh is can also do all these different matrix operations, and a mesh is also the model, the world, and the screen are all kind of the same type of mesh. They're just a collection of points in a vector, or they're actually collections of polygons that each have 3 points in them, the triplets of points. So we got our textures we talked about, and there are the triangle, let's say the bottom corner of that up sign, and that gets painted on a rotated and distorted triangle of the side of the up on the cube. As you rotate them, they effectively get stretched. However, we don't stretch this triangle. We know that each of these points in the triangle that has a surface, and I call these the surface 0, surface 1, surface 2, those map to what the points were on the cube of 0.1, 0.0, 0.1, 0.2. But there's a rule for this. So you got the points that go in this direction. If you take your fingers and you wrap them in the direction that they go around that triangle, your thumb will be pointing up. When you go to paint it on the surface, that's the direction of the up that your fingers curl, so it's forwards. Here, we actually assigned it to a cube and did it backwards. So our fingers curl, we have to turn around, and our fingers curling is the way that it's curling there. The thumb is pointed away from us, so that image is actually backwards. We're looking at the back of the surface that we're painting on there. And so in this case, the word up is backwards. And you'll see that how, show you an example in the demo later of how you can see the backside of some of these objects. Okay, so we have two different types of buffers. We have an image buffer that we actually paint the image into, and then we have a Z buffer that handles the depth, also called a depth buffer. It's more of considered in just grayscale because it's just a measurement of how close it is to us. As we're going through rasterizing, we're going to take every point that we're looking at and say, how far away is that point from me? Is what I've already painted on the screen further away or closer? If it's closer, the point I have is behind it. It's hidden, so I don't paint it. If it is closer, I would then paint that pixel. You can also do some Z clipping at this point for if that's further away depth than you really want to handle or not. I don't bother with that just because of my simple examples I'm doing. But I'll show you, I actually have a way through my application, my little test app, that will show you what the Z buffer looks like, and you can see the different depths on it. So we've seen this before. It's the 1 by 1 by 1 cube and the surfaces for it and how the surfaces are painted on there. So when we go to paint this triangle here, which maps to these coordinates here, there's two things that we need to take care of. Each color for each pixel on every point in there, and the depth to figure out if we actually even want to paint that or not. But we don't know what the depth is in the middle of this triangle. We only know the depths at the points we had defined. So when we've rotated things around, so this point might be at one particular depth away from us, and this one may be, because it's angled away, maybe significantly further away, so it has much deeper depth. So we basically need to do a linear interpolation between here and each of the points, and know we're 75% of the way between these 2 points, therefore the depth is 72% of the way. And as we're going through this and painting this, we start with these two edges, and we go between every point, pixel by pixel, on every line, each raster. That's why it's called rasterization. And so it's the top point to the point on the left and the top point to the point on the right across step every single pixel. Then that's with every single pixel that's on our screen in our bitmap that we're going to be looking at. So we have our depth. We know our points. Each one of those has a depth. For convenience and mathematical simplicity, I cut this triangle in half and make two triangles. And so I rasterize between these two lines all the way across, and then these two lines all the way across down to the same point again. So interpolation, we know the depth here, we know the depth here, we know that we're some percentage of the way down. We also know that when we're going level across here on the screen, that's going to intersect at this point over here. This point is a percentage of the way between here and here. Here we know the depth, here we know the depth, so we interpolate here. So as we're going across the screen pixel by pixel, we interpolate again between the depths on either side. And that tells us what the exact depth is at that point. That's when we make the decision, is that depth further away or closer than what may have already been at the depth? If there was never anything painted there, there was no depth. It's kind of an infinite distance away. We then painted, and we add ourselves to our depth buffer. At that point, we also add ourselves to the color of the image buffer, but for that, and that's putting the bottom half of the triangle, and that would make a grayscale depth, how far away we are. But now we need to do the actual image of the surface that we've painted on there. Same rasterization, and we're doing a similar interpolation of how far down the sides we are straight across, but now we have our triangle from the source. So this point is in 3D space, this point's in 3D space, and this point's in 3D space, but they align with this point, and this point, but you notice it's stretched. So the diagonal line where we cut this in half is a certain percentage across here. That is what would be equivalent of across here. So as we are tracing, we're in the bottom half of the triangle now, and we've interpolated across to here, and we're going straight across here. That now maps to this percentage across here and this percentage across here, and now we interpolate across the middle again, and so that means we're this far across, and so we know at that very particular point, we've now gone from yellow to red, and so we would be painting the red that's at that pixel point. And we would end up with, so we had our mesh, and as we're rasterizing this is made up of 12 different surfaces of the triangle, and we iterate through each of those the triangles that are on there and paint those on, and we end up with something that looks like our cube. There's a mathematical problem that happens though because of the interpolation we're doing. When our grid is flat and we're interpolating across this triangle here, everything looks fine when we're perfectly flat. But when we start twisting this at an angle, that triangle there is this triangle. And if we go, say we're going 10% down on this side to the 10% point on the hypotenuse, or the long side here, everything fine. It's 10%, 20%, the interpolation works fine. But then when we're doing the other side of the triangle, we go from the 10% point to the 10%, 20%, 20%. You notice these lines do not line up, and there's a mathematical error in that. And so there's a way of correcting for that. Even though we've only ever defined this triangle having 3 points, you can imagine there's a fourth point hiding out there. And when you go to twist this thing, Your furthest away edge is going to be narrow, but your closer edge is actually going to be much wider. And that's why the slope, the diagonals we had on there from the 10% to 20% points failed. This imaginary point, if we were to have kept track of that and run it through all the same matrix transforms as an imaginary cube, this point would map to this point, and we could easily do the 10% there to the 10% there, 20% there to the 20% there, and that would even this out such we wouldn't be getting that funny error of where they were colliding together at sharp angles. This is the entire example of my pipeline in my application. I have a model passed into me. I scale it and place it. I rotate it. I make a copy of it. I place it. I rotate it again. I place it. Or actually, pardon me. I made 3 different models. I rotate and translate for 4 different depths. Each of these rotate on an X, Y, and a Z. And the last one, mathematically, in theory, kind of impossible. I rotate it on the X, Y, and Z axis. But remember, matrix operations happen in order. It rotates on the X, and then the Y, and then the Z, and then I move it. And so as I added each one of these models, as I've multiplied them out, I add them to the world. They just become more collections of points in the world. So, and I get the point of view, field of view, and viewport, multiply those together, and multiply that across all the points in the world, and that becomes my screen. Then I do that perspective divide. That's where we go through and divide every point, every X, Y, and Z by the W. And then I get my screen. And this is my mesh of coordinates that have been retranslated to the camera view and what the camera up is. And all the points have been flattened. So the X and Y are X and Y from the perspective where the camera is, and the Z is the depth of how far away it is from each of those points. So this would be the depth of my 4 different objects. Some of them, they have all been rotated. Some are further, some are closer. In my application, I happen to show closer numbers as darker. There again, that's just my mathematical way of keeping track of it. And then this is how each of those surfaces would be painted. Yellow doesn't give a whole lot of differentiation, but the Earth, like the oceans kind of overlap, and so you don't get a whole lot there. I'll show you some better ones. Demo. This is the wireframe of what's generated and each of the triangles that's with each of those. This is the depth buffer of actually as they're being drawn. And I'm a geek, so I go for the numbers. This is drawing 30 frames a second, and it is processing 30 million pixels per second. As it's rasterizing across each one of those. Each one of these cubes has 12 big triangles on them that take up a lot of area. And so as I'm going across rasterizing every one of them, including all the hidden sides, because you don't know it's hidden until you've actually rasterized across it and look at those points. This is a single-threaded application that is running so it's on one core. It's 1/8 of the processor in this machine. And I'm running, it's at full HD. And this is the image that's on there, the up. Okay. You've seen the Earth that we were showing. This is Frankie. Frankie is my puppy who's no longer with us. But that interpolation error type thing that I was talking about, I was looking at him and I'm going, is it an optical illusion, or is his nose moving as he tilts? And it turns out it actually is, his nose is tilting because of that perspective divide. As it's hitting at angles, it's being drawn at slightly the wrong place. And you can see it in here, and let's slow this down so you can see it a little better. See, when it's flat, it looks just fine. But as it starts getting to get sharp angles, you see the diagonal across, the perfectly square. Now the diagonal across here is looking like they're leaning in towards each other. There is another form of 3D math for locating, rather than doing straight interpolation of what pixel you grab out of the surface, that deals with some math that I don't understand. But basically, you have our 3 points of our surface and our 3 points of our triangle, and it does a equal distance ratio mumbo jumbo between these points, and it's basically the distance or vector from each of the coordinates of the corner points, and it comes up with a equilibrium point from a different triangle, and that's the point that it goes to get it out of, and it doesn't have to deal with that interpolation error. Now I mentioned I was going to show you. Okay, well, here's Frankie again, and this is mixed. This is half of the up cube and half of the Frankie cube. Let's make this a little bigger so you can see it better. You can see edges collide as they go through each other because there's no surface tension. These are surfaces in our mind only. These are not real hard surfaces. The human mind is used to seeing when two cubes collide, they collide and they don't go through each other. But if we were to leave half of Frankie there and get rid of all those ups, we can see through the cube, and we can see these edges intersect with each other, like right there, and some of the points there. And it can really get hard on our eyes, almost like daggers of the mind, to see these things intersect with each other and collide, and it becomes really hard to envision. Now, I talked about looking at the backside of a cube. See, without the surfaces in there, we can see through and see as this surface is being painted, we can see the opposite side of the cube over there, and because some surfaces were using the winding one way versus the other, if you realize this was the back side of the surface, this is actually showing Frankie facing two different directions. One is because he's looking this way, and actually these both look like his nose is going the same way, but we're looking at the back side of it. As this cube rotates around, now he's actually facing the other way. So surfaces are more like a painted cellophane where you can see through them. What else did I want to show you in this? With the depth buffer, you can see some of the collisions that are happening here again also. Now the offset is how far these cubes are away from each other, and the scale is how big they are. So you can see some of the edges colliding through on the depth with each other, and then you can kind of envision of why it looks like they're colliding, because when they're at the same point, the depths look the same. But when you can see through it, you can see the depths that are further behind or not slicing through this. And if we go back to the image, very confused image. Solid surfaces here, we can see the cubes of the Earth that are colliding with each other and going through each other. Okay. Some potential, that was all handled single threaded. Let me check my time here. Oh, I think I'm running short on time, I believe, here, but I'll make it quick. And that's because I had one big buffer that was the size of the screen that I was painting into. Another way to do this faster would be to take each one of the triangles, the polygons, and paint them into their own surface and depth buffer. And then go and combine all of those together. But we end up with a couple of problems. As we combine all of them together, say we're doing this we painted each one of these in their own thread, and then we throw them into a collection, and we then share them out to each individual threads, and each thread then multiplies them, joins them together, and joins them together, and joins them together. In theory, that seems like it'd be fast. We subdivided the work. We're doing it across 8 different cores, except each one of these, the bitmap images, has a significant amount of memory of both the image and the depth buffer, which is effectively a monochrome bitmap. And when you move these from one thread to another, it takes a long time to load that memory in the other thread in the cache, and the CPU takes a long time to move these things back and forth. So a way to get around, potentially get around that. Actually, this one was showing joining those all together. Another way to do that would be take some of all these triangles and put them in each different threads, and then you have a full image that you add the triangles one at a time, doing this in multiple different threads. Then you finally join the data together from all the threads, and you end up with our final painted object. Running short on time, so I'm going to kind of skip some of this. Texturing the image can be at multiple different scales. Sometimes they'll actually pre-draw these at multiple different sizes, so you get to choose which one you're out of and which one would be the sharpest image to deal with. You also dealing with, when you are looking at a particular pixel and the interpolation in the surface, are you actually looking at a single pixel, or are you looking at what covers multiple pixels that are actually straight up aligned? So this is assuming it's a single pixel. This is a region of pixels that kind of averages the color. This one also covers a multitude of pixels in the actual surface and picks the average color there. This is showing how it would do some of the average interpolations. Questions? Yes?
Can we connect with you on LinkedIn?
Yes. Right there. Yeah. The source code for this and a copy of the slides in PDF format, you can get them from that teeny URL. I am on LinkedIn. Make sure to send a comment. I get hundreds of invites a day, and if I don't know who it is, and if they don't say how I know them, ignore. And if I mark you as I do not know, LinkedIn has a ranking score, and if you get too many I don't knows, they will, battery running. I'm plugged in. Okay, maybe I'm not. I guess that's the end of my presentation. Thank you very much. What was I going to say? LinkedIn, if you get too many of these I don't knows, they may suspend your rights to invite other people to connect. I think they've gotten a little bit away from that, being that they just realize that it's all part of the pyramid scheme and they want more and more people. So, more questions about any of my weird math that is doing on this? Oh, this application saying 56K, single-threaded application handling, even if on a bigger machine at home, it can handle 60 million pixels per second at 60 frames a second. Laptop's a little underpowered, so it still only does 30 frames a second at full HD. So.
Do you have any plans on running on the GPU?
I've thought about that. As it turns out, the matrix multiplications and all that is actually very lightweight. First of all, I don't have that many points on my screen. If I had thousands and thousands and thousands of points, that might become a little faster. But because you multiply all your matrices together first, then multiplying that across the mesh is still relatively lightweight. And you'd probably spend more time copying it in and out of the GPU than it would be worth. Most of the time is spent in rasterization of interpolating and going down every single pixel. Follow up?
So for your use case, it doesn't really make any sense to go GPU then?
I could. It doesn't. I don't think at this point. Game engines, definitely, they have determined that it makes a difference for them. They're dealing with a lot more points than I'm dealing with just for my simple little demo app on this. Yes?
Have you considered using it for a game or something? Just to test the abilities?
Yeah. I'm breaking one of my own rules. Yeah. Well, two things. The speaker should always repeat the question back. And so he was asking back there if I've considered porting to GPUs. And then you were asking about alternate uses if I ever have thought about writing a game or doing that. I don't have that level of imagination. I'm very orthogonal. I draw squares. I've tried to do some of this with a dodecahedron, 12-sided object, and wrap a globe with that. I was having problems with coordinates and visualizing that. So I have more questions. Okay, the other question, the rule that I was about to break, is of going over. You can never go over. You guys deserve your break. So I will take questions off tape here in a minute if people have more, and we can talk about. So thank you very much.